There is no doubt that the effects of climate change have already begun to show themselves.
Pakistan, it was the hottest April.
Europe is sweltering.
Australia's worst bushfire season on record.
And while most countries are taking small steps towards reducing their emissions, it's unlikely that society will reach a carbon neutral state at any point in the near future. This has left scientists and engineers thinking of a way to address climate change without relying on emissions reductions. Enter the field of geoengineering, a relatively new school of thought that envisions ways to reduce the average global temperature through artificial means. While this idea is not without its controversies and knowledge gaps, it does tentatively provide us with an almost immediate solution to an emerging global crisis. Solutions that, if executed properly, have the potential to stop global warming altogether. When it comes to engineering a solution to climate change, there are two main paths that have received the most attention. The first is known as solar radiation management, or SRM. This is essentially limiting the amount of sunlight that reaches Earth's surface, thereby cooling the planet. But not in some evil Mr. Burns way, but by filtering out small portions of incoming sunlight on the magnitude of 1 to 2%. These strategies can easily offset the warming caused by a doubling of Earth's CO2 concentrations. The second path is greenhouse gas removal, or GGR. This involves removing the excess CO2 in our atmosphere by speeding up natural processes that sequester carbon. These strategies can be as simple as planting acres and acres of trees, or as complex as making an arsenal of carbon capture facilities. 5 of the most prominent ideas are stratospheric aerosol injection, marine cloud brightening, sunshades, ocean alkalinity buffering, and ocean iron fertilization. To make sure these topics get the attention they deserve, I will be breaking up the research into 3 videos. The first video will cover the leading ideas for solar radiation management, the second will cover greenhouse gas removal, and the third will address the cost, concerns, and uncertainty of each of these strategies. Make sure to hit that subscribe button and click the notification bell so you don't miss parts 2 and 3 of the series. While no geoengineering strategies are inherently perfect, all have the potential to ameliorate the worst effects of the climate crisis. Let's start by taking a closer look at how stratospheric aerosols could undo global warming. The basic idea behind stratospheric aerosol injection dates back to as early as the 1970s. Russian climatologist Mikhail Budiko proposed that if global warming ever became serious enough, humanity could just send a fleet of airplanes into the stratosphere to spread out aerosols and scatter incoming sunlight. Today, that principal idea still stands, as we have clear evidence that stratospheric sulfate particles are great at scattering sunlight. A prime example of this happening naturally was the eruption of Mount Pinatubo in 1991. This single event is estimated to have pumped 10 teragrams of sulfur into the stratosphere in just a few days. Over the next 15 months, scientists were able to see a drop in average global temperature by 0.6 degrees Celsius. This occurred because the particles shot into the stratosphere were effectively blocking sunlight from reaching the Earth's surface, thereby cooling the planet. This has inspired scientists to consider an artificial injection of sulfate into the stratosphere to achieve a similar level of cooling. By aiming for the stratosphere instead of the lower atmosphere, the particles will stick around longer without things like rain pulling them back to the ground. Delivering these aerosols would require a special engineered fleet of aircraft unlike anything currently in existence. They would need to be capable of reaching the high altitude of the stratosphere while carrying massive sulfur payloads on the order of tons. These aircraft would need to constantly make flights across the globe in order to loft enough sulfur into the stratosphere to have a noticeable effect on the climate. Even a conservative approach to stratospheric aerosol injection would require 100 million kilograms, or 0.1 megatons of sulfur, just to halve the rate of temperature increase. More aggressive plans can push this value much higher in order to return Earth's temperature to pre-industrial levels. As you can imagine, this strategy is not cheap. Designing the aircraft, producing their payload, and fueling them to fly into the stratosphere thousands of times a year would cost the world billions of dollars. However, the cost of inaction on climate change is orders of magnitude greater than this, providing an incentive for the world to pursue this idea. Now let's take a look at an idea that's much more down to earth. Marine cloud brightening is an idea first postulated by John Latham in 1990 to raise Earth's albedo by artificially increasing the cloud cover over the oceans. For context, albedo is a measurement of something's reflectivity, with a pure black object having an albedo of 0 and a pure white object having an albedo of 1. The higher a planet's albedo, the more sunlight is reflected back into space and the cooler the temperature. Low-lying marine clouds already reflect sunlight naturally, but marine cloud brightening proposes a way to artificially generate bigger, brighter clouds. This is by seeding clouds with seawater aerosols that are generated at the surface. As these particles drift upward into the atmosphere, their water evaporates, leaving behind tiny salt crystals to act as cloud condensation nuclei. These are particles that water molecules can accumulate on to form the tiny suspended droplets we see as clouds. This higher concentration of condensation nuclei leads to brighter clouds that reflect more sunlight, raising Earth's albedo and cooling the planet. To get these particles into the atmosphere, specialized ships would pump seawater through an atomizer to create a fine mist of particles. These could then be lifted higher into the atmosphere with fans on the ships to reach elevations where they could enhance cloud albedo. Using climate models, the amount of sea salt aerosols needed to offset a doubling of atmospheric carbon dioxide is around 50 to 70 teragrams of salt in the most efficient scenarios. While this may sound like a lot, it's actually only 10% of the natural sea salt aerosol formed from crashing waves in the sea breeze. Future studies that analyze marine cloud brightening's effects on local precipitation, coral bleaching, and polar sea ice may prove this idea to be a golden solution in fighting climate change. But what if we could reflect this sunlight before it even reaches Earth? There are proposals for a solar radiation management strategy that involves scattering sunlight in space before reaching Earth. While geoengineers have developed several ideas for this, the most plausible strategy would be a large sunshade that reflects a small fraction of sunlight away from the Earth. This could either be achieved with one massive megastructure, or more likely a swarm of miniature ones that cover the same area. These miniature sunshades would be launched from Earth to a point between the Earth and the Sun known as Lagrange Point 1, or L1. This is one of 5 points in space where the gravity from the Sun and Earth and the centrifugal force all cancel out, about 1.5 million kilometers from Earth. Here they would sit in a stable orbit, blocking out sunlight before it reaches Earth, shading the planet and cooling it down. However, there's a lot more going on here than meets the eye. First, how big would the shade need to be in order to cool the Earth from space? If we were to freeze the solar system and just pin a giant sunshade right at L1, it would need to be 1,830 kilometers wide. That's about the distance from Madrid to Berlin. So yeah, we're talking about a huge shade. However, the solar system is not frozen. The photons coming from the sun each carry a tiny bit of force that, when added up, can push on objects in space. This is known as solar radiation pressure, and it would send our sunshades spiraling back to Earth. To accommodate this, the shades need to be placed closer to the sun so that its gravity pulls harder on them and balances the pressure. How much closer depends on how heavy the sunshade itself is. While this estimate can vary depending on people's optimism for future technology, the best case would be at a point 2.44 million kilometers away from Earth, 63% farther from Earth than L1. This new L1 prime is not good for the overall cost, because a larger distance means that the sunshade will need to be larger to block the same amount of light. The new sunshade diameter at L1 prime would have to be an astonishing 2,868 kilometers wide, nearly the distance from Madrid to Kiev. To make something this enormous requires a lot of effort and energy to both make the shades and send them into orbit. Assuming a launch cost of $50 per kilogram, $1,000 per sunshade, each weighing about 55 to 80 kilograms, and additional costs in development, launch sites, and launch vehicles, brings the total cost of such a project anywhere from $3 to $7 trillion. That's quite literally a shit ton of money. A project of this magnitude has never before been attempted, but the price isn't actually a total deal breaker. This project would be spread out over roughly 20 years, amounting to a few $100 billion of investments per year. While this still may seem like a lot, and it is, climate policy analysts project that the damage to global GDP without any action on climate change could be even higher. 2.5 to 3 degrees C of warming by 2100 could cause anywhere from 46 to $227 trillion in lost revenue. This is far beyond the cost of a full-scale sunshade deployment, but still sunshades are most likely not a near-term reality. However, these would be the ultimate geoengineering devices, allowing us to control the sun's luminosity like a dimmer switch, and even allowing a concentration of shade in particularly sensitive areas like the polar ice caps. They may be a long ways away, but there is still a possibility that we see a project like this developed in our lifetimes. While the idea of geoengineering is fascinating, as humanity has never directly tried to change the climate, it's only a reality because humanity will not stop indirectly changing the climate. These propositions are only now becoming attractive because the climate crisis worsens every passing year. The most effective means of controlling the climate is to reduce greenhouse gas emissions as swiftly as possible. However, it's at least comforting to know that even if this does not happen, humanity has a plan forward that allows us to stabilize a destabilized system. As computer models and our understanding of Earth's climate progress, geoengineering has emerged as a solution to potentially put an end to climate change as we know it. Thank you for sticking around to the end. Comment your thoughts on geoengineering and whether or not you think it's a good way to address the climate crisis. Stick around for the second part of the series where we dive more in depth into greenhouse gas removal strategies. As always, the sources are linked in the description if you want to read more about SRM technology. If you enjoyed this video, make sure to like, comment, and subscribe to support Planet Zero. I'll see you next time.